Hello everybody, my name is Narpinder Kaur. I am a graduate student working with Dr. Naresh Dalal at the Chemistry Department of Florida State University. Today I would like to talk about a part of my PhD dissertation. My talk is about quantum phase transitions in compounds containing two unpaired electrons, that is spin 1 compounds. The compound studied was diperoxo diethylene triamine chromium 4, and here I show the model of this compound. The structure of the compound consists of a chromium 4 3d2 spin 1 center, which is shown by the yellow ball here, and it is bonded to two peroxo groups. The red balls represent the oxygen atoms of the peroxo groups and three nitrogens of the diethylene triamine ligand. It should be noted that chromium 4 is a rare oxidation state of chromium. The compound was synthesized by the reaction of hydrogen peroxide with aqueous solution of CrO3 and diethylene triamine as shown in the slide. Large single crystals of several millimeters were grown by evaporation at room temperature. X-ray diffraction data showed that the spin structure of the compound forms a two-dimensional square lattice, and our goal was to investigate this lattice from the point of view of quantum phase transitions. The major techniques we used to study this chromium-diene system were torque magnetometry, heat capacity measurements, and magnetocaloric effect measurements. And in today's talk, I would focus on the heat capacity and the magnetocaloric effect measurements. In the next slide explains what the quantum phase transitions are. A quantum phase transition is a phase transition which occurs at absolute zero temperature as we change a parameter, which could be the magnetic field or pressure or the chemical composition. Now, an important question which arises here is, how does a material behave as it approaches a quantum critical point, that is a quantum phase transition at t equal to 0. And in this regard, we did the heat capacity and the magnetocaloric effect measurements at National High Magnetic Field Laboratory in Tallahassee, Florida. The measurements were performed on SEM1, on which we could achieve a magnetic field of 18 to 20 Tesla can be achieved. Using the dilution fridge with this system, we can get to the lowest temperature of 20 millikelvin. And here is our heat capacity versus temperature plot. As you can see in this plot, the transition temperature increases with increase in the magnetic field till 5 Tesla. With further increase in the magnetic field, the transition temperature starts decreasing. And if you look at the 12 Tesla peak, it's very diffused. So from here onwards, we decided to switch from heat capacity to the magnetocaloric effect measurements. This figure shows typical peaks from magnetocaloric effect measurements. The red curve was obtained by sweeping the magnetic field from 11.5 to 13 Tesla at a fixed temperature, and the blue curve was obtained by sweeping the magnetic field down from 13 to 11.5 Tesla at the same fixed temperature. The temperature corresponding to the average of the two peaks was taken to be the transition temperature. And here is the H versus T plot, which has the combined results from both the heat capacity and the magnetocaloric effect. As you can see in this plot, it is non-linear in nature with respect to the magnetic field, and with the transition temperature first increases with increase in the magnetic field, and then it starts decreasing. The Néel temperature approaches absolute zero at about 12.5 Tesla. So here our goal was to understand the behavior of a phase transition as the temperature approaches T equal to 0. So we decided to fit the lowest temperature data between 0.2 to 20 millikelvin using the power law shown here, which is H minus Hc equal to B into T raised to the power alpha, where Hc is the critical field, T is the transition temperature, and alpha is the critical exponent. We fix the value of alpha equal to 1.5, and then we fit the power law to the magnetocaloric effect data with Hc and B as the fitting parameters, and the values of Hc and B obtained from this fitting correspond to the transition temperature labeled as T max in the plot. Then this transition temperature, which is labeled as T max, is deleted, and the power law is fitted again to the rest of the data to obtain new values of Hc and B, and we repeat this procedure for all of the data. And here we plot the Hc, that is the critical field, versus the transition temperature for different values of alpha. We took alpha equal to 1.5, 1.75 and 2. The data shown by the solid circles was used for further analysis, because as you can see, the data beyond 1.2 Kelvin, the data starts deviating from the linear behavior at low temperatures. We did straight line fit to the data, to the critical field versus transition temperature data, and then we extrapolate each curve for different value, each Hc versus T curve obtained for a different value of alpha to T equal to 0 point to obtain the critical field value for that particular alpha. And thus we get 3 critical fields for 3 different values of alpha. The final critical field value is obtained by taking the weight average of these 3 critical field values, and thus our final critical field value was 12.392 plus minus 0.003 Tesla. Once we obtain Hc, we fix the value of critical field in the power law, and now by keeping B and alpha as the fitting parameters, we do the same regression analysis. And here we get the values of alpha plotted against the transition temperature. The data shown by the solid circles, which are not deviating much from the linear behavior, we take the weight average of them to find the final value of alpha, and our final alpha value is 2.01 plus minus 0.02. Finally, by fitting the power law to the magnetocaloric effect data, we get the fitting parameters, and then our fitting curve comes out to be as shown here. Now the point at which the point on the y-axis at which the red curve meets the point at which the red curve meets the y-axis at t equal to 0 and a critical field of 12.392 Tesla is our quantum critical point. Another thing to be noticed here is that the red curve starts deviating from the measured curve beyond 1.2 Kelvin, which shows that our quantum critical regime exists only about 1.2 degrees within the absolute 0. In conclusions, our measured value of alpha equal to 2 suggests that chromium-diene is an Ising magnet. This was an unexpected result because chromium-diene showed two-dimensional behavior at high temperatures. Further studies are being carried out to understand the origin of this Ising behavior. And thank you for